Good afternoon, everyone. Today we have new sessions. I opened Pandora's box and it was full of obfuscations. Today our speaker, Geri Revay. He's from Fortinet. Geri has more than 13 years of experience in cybersecurity. He started on his path and he's specialized in network and information security in his master in computer engineering. Since then, he was worked as a QA engineer for security vendors. Then changed to penetration testing first and external consultations, and then as internal consultants at Siemens. He is a hacker at heart and a consultant by trade. He worked on both IT and OT systems. In the past years, he focused on security research and binary analysis and reverse engineering, which led him to Fortinet. At FortiGuard Labs, he currently does malware analysis and reverse engineering related research. Please welcome Mr. Geri.
Thank you. You can hear me, right? Great. Yeah. So, thank you for coming to my presentation. I'm going to talk about the case where I opened Pandora's box and it was full with obfuscation. I come from, Fortinet, FortiGuard Labs. I think there's not much more need for introduction. In my spare time, I like to collect certificates. All right, so a little bit about the agenda of this talk. First, of course, we are going to do some introductions, not me, but the topic. Then we are going to talk about obfuscation techniques in Pandora. The main topic we're going to talk about is control flow flattening and using emulation to deal with control flow flattening. And of course, at the end, we will have some conclusions. All right. So, introduction. You might have seen this slide or a slide similar to that because they come and go everywhere. The reason I brought this up is because I think it's important to talk about the background of obfuscation and why we need to talk about obfuscation generally. And what I think one reason that obfuscation is becoming more and more important for us is how the cybercrime ecosystem is changing. So I think everybody is aware that nowadays cyber criminals are starting to focus on different parts of the whole attack. So if you're a newcomer, a criminal, then you can just buy your credentials from an initial access broker. Then you can buy your malware from a malware as a service provider, and then start doing your criminal activities. And the reason why this is important in terms of obfuscation is because this model that started to be built allows the different threat actors to focus on a single objective instead of taking care of the whole attack kill chain. Let's put it this way. So when we talk about malware as a service, then malware authors have now the incentive to try to create more complex and better malware. And one way a malware can be better is that it's more difficult to analyze, and it allows their users to get away with using the malware for a longer time. So because of that, basically this malware as a service model allowed the malware authors to include more defense evasion techniques, more obfuscation, etc., etc. Generally try to create more complex and more difficult malware. Just to underline this with some kind of statistics, this is the data from the FortiEDR telemetry, and what's important here is that on the list of tactics, you can see that defense evasion is on the top of the list, which kind of shows us how much malware authors are investing into creating malware that is capable of evading defenses. This is kind of like the background story of obfuscation. A few additional points to why to talk about obfuscation is that generally, it's not a silver bullet in terms of usefulness for the attacker. It's more a ball and chain for the analyst. So it's very cheap for an adversary to implement obfuscation because there are plenty of ready-to-use tools out there, and obfuscating the source code takes around like 5 seconds. If you want to do some QA, then it's going to take maybe an hour to make sure that it's still working. It works on multiple levels, so it's very easy to implement obfuscation for attackers. However, it's going to cost much more time for the reverse engineer or for the analyst to actually figure out what's happening in that malware. And it works, yeah, I said it works on different levels. There is obfuscators for most of the programming languages out there, so whatever criminals are using, they can find an obfuscator ready to be used. Because of our example, which I'm going to introduce in the next slide, we're going to focus on C++. By the way, an announcement, because it's after lunch, and this is a very technical topic, if you feel like you need to close your eyes to better understand what I'm talking about, you're welcome to do that. So. Yeah, so our use case is going to be the Pandora ransomware, which I looked at last year. And it was kind of a generic ransomware in terms of functionality. It had everything what a state-of-the-art ransomware needs to have. It had multi-threading, strong encryption, disabling AMSI, disabling event logging, using the restart manager to unlock files. So generally, it was very round ransomware, and it also contains all of the words evil, and that's what we are going to talk about. So obfuscation techniques in Pandora. So generally, it was full of obfuscation, as you could realize from the title. This is just an overview, and we are going to go through some of these topics. So it had a custom UPX packer, which it wasn't really a big challenge, but it was not off the shelf. It had string encodings. The interesting part that it has 14 different decoding functions, which kind of made the decoding a little bit more challenging. The functions were pretty much the same with slight changes. It's just the fact that there were many of them was a bit more challenging. There was cold address obfuscation with opaque predicates and jump address obfuscation similarly, which I will talk about in the next slide. And then control flow flattening and also Windows API call obfuscation. So there were a bunch of annoying stuff generally. So opaque predicates in call and jump addresses. So if you're not familiar with the idea of opaque predicates, it's basically obfuscating something static just by adding some calculations to it. So for instance, if you look at the assembly code, it adds in a call RAX, and the address that's going to be called is going to be calculated in the instructions above the call. So above that, you can see the equation that is used to calculate the addresses. So there's an address table, and then there is an offset, and there is some additional additions just to make it a little bit more complex. But generally, there's everything in the assembly code that needs to be used to calculate the address. So the address is fixed. It's not going to change in runtime. But because it's calculated in runtime, it makes disassembler's job much more difficult. And a good example, so the control flow graph that you can see below, that's from Pandora. And so the same thing is done with the jump addresses. And what's happening here is that you see all those basic blocks on the top that are not connected to anything. The fact that they are not connected is because of the jump address obfuscation. Because IDA cannot recover the address where those jumps are pointing, so it cannot connect the basic blocks to the next basic block that they're supposed to come. When we talk about the call address obfuscation, the result is that there are no cross-references in the binary. So when you're playing, looking around in IDA Pro or other disassemblers, you can't just come and go between functions because there are not going to be cross-references from function calls to the actual function that is being called. you need to recover that in some way, which I'm also going to talk about. And control flow flattening, as I said, this is kind of our main topic. If you're not familiar with that, a little bit of an introduction. The general idea is that we are trying to surprisingly obfuscate the control flow of a function. So it's applied to functions separately. And so the image is from Tigress. That's an open source obfuscator. If you have time, it's worth to play with it. And what you can see on the left side is the original control flow graph. And when you look at it, although we don't know anything about this function, we can still figure out a lot just by looking at it. There is some decision in the middle, there's a loop, it goes back, and at some point the loop ends and it goes to some kind of end state. Now, if you apply a control flow flattening on this function, you get the control flow graph on the right. Not surprisingly, it's flattened. So basically, all the basic blocks that have the useful code is on the same level. And it implements a switch case state machine. So usually there's some kind of state variable, and there's a dispatcher, a set of basic blocks that implement the dispatcher, which is going to decide which basic block should be executed next. So which is the next state. And the problem is that when we are looking at this function on the right, we don't know anything about this, especially if all the functions are flattened, then all look similarly, just they have more or less basic blocks, but their structure is exactly the same. And for instance, this is important in cases like I talked about the 14 different decryption functions. Once I saw one, I could recognize a decryption function just by looking at the control flow graph, because it was the same thing, just maybe the parameters were different. Because it wasn't flattened for whatever reason. But because of that, every time I saw a new decryption function, I knew it immediately that it's a decryption function just by looking at the control flow graph. And I didn't need to reverse it. If they had flattened those as well, I would have needed to reverse all those functions as well, just to figure out that they are the same as all the others I've already seen. Just a bit of vocabulary. So when we talk about flattened function, the original basic blocks are the basic blocks in the middle that contain the original logic of the function. And the dispatcher basic blocks are those that are responsible to managing the state and which basic blocks should come next. So these are the two main structures of a flattened function. And just a few examples from real life. So on the top, you see a normal function. Again, we don't know anything about it, but we already see there are a couple of decisions, there are two loops. So you already know something about it. And then once it's flattened, you see the one below. And I don't know what you're feeling about this function, but it's not encouragement to start reversing it. This was my real life feelings on one of a sample I looked at. That was actually .NET, so it's a .NET file open in IDA. But it's welcome to hell. So it's not like I really wanted to go further than this at this point, but yeah, I needed to. So how can we deal with control flow flattening? So from the emotion side, pack up your stuff and run. All right. But obviously we can't do that all the time. So we do need to figure out some strategies. And there are a few things you can do, both statically and dynamically. So first, statically, we can try to restore the control flow, for instance, by implementing some kind of IDAPython script. To do that, we can use like generic pattern matching to recognize the different basic blocks and figure out what the original control flow was. We can use emulation, which I'm going to talk about, and we can also use symbolic execution, which is often used for this, but it's it's a mouthful of technique to use. So it has its disadvantages as well. When we talk about .NET, some deobfuscators work. So .The can deobfuscate some obfuscators. I've seen a presentation about writing plugins for .The to restore control flow graphs. So that's also possible if you start writing plugins. In practice, like if you have a time limit, which obviously you often have when you're doing reversing, dynamic analysis could be very useful. Sandbox detonations will still give you really good IOCs because it's just obfuscation. So the IOCs should pop up at some point. Debugging is really useful. It's just very tedious because you have to click through all these control flows where you don't really know what's happening until it happens. So it's just a pain, but it's doable. Okay, so if we try to actually restore the control flow, this is the generic method of what to do. So first we want to identify the dispatcher basic blocks. So basically the basic blocks that are responsible for managing the state of the function. Then we need to identify the original basic blocks. That's usually pretty simple because those are the long basic blocks because that's where actually something happens. And usually they end in one basic block. So at the end there is always one basic block that's going to take the control flow back to the dispatcher blocks. And then you need to identify the state variable. Sometimes there's just a very simple state variable, either a register or a local variable, which have, maybe it's just an integer that's being tracked, but maybe it's like there's like a state table or something like that, and then you see offsets. Pandora was relatively complex from this perspective as well, but some samples are much more easier in terms of state variable. And once you have that, you can easily map the states to original basic blocks. And once you have that, you need to see what the next states are for each original basic block. So it's either one state, if it would be just a simple jump to another basic block, then it's going to be just one next state. But if there is some kind of conditional jump, then it's going to be two states. And if you identified all these, then you pretty much have everything to reconstruct the control flow. You either just print a graph and look at it that way, or you can try to patch the IDB in IDAPro, or patch the binary itself with some other tooling. Yeah, just a few examples for this in Pandora. So when we talk about finding the original basic blocks, or no, the dispatcher, I'm talking about dispatcher here. The dispatcher is all the basic blocks on the top, because those are that once you debug it a little bit, you see it quickly. But those are that don't do anything else. Just look at the state and decide where to continue. So if you look at the assembly, there is some kind of compare. There is some kind of conditional move that's going to move the address of the next basic block to the register that's going to be used in the jump. And these are the two different basic blocks in Pandora that you can see as dispatcher decision blocks. So using these, we can build some heuristics. So for the dispatcher blocks, we can figure out that there is some kind of conditional move or set that's going to set the register. There is either a compare or an XOR, and a compare after an XOR if that's the case. And using that, we can create in an IDAPython script, we can create this pattern and look for basic blocks that match this pattern, and this way we can identify the dispatcher basic blocks. As I said, the original basic blocks are much more easier. If I go back a little bit, you see that all the long basic blocks are the original basic blocks, because that does the logic of the original function, and they all end up in the same. They have a direct jump to the last basic block that's going to take it back to the dispatchers. So here in the middle, you can see the end of an original basic block. It's going to jump directly to that one basic block. So it's not going to be a jump to some register. It's going to be a jump to a direct address. Yeah, and to the dispatcher basic blocks, the end is always a jump to register. But again, this is very specific to the malware, so this is the disadvantage of trying to do pattern matching in our script, because it's going to only work for this specific sample. Decision basic block, this is just something interesting from the logic of the obfuscation. So if in the original code you have a decision in the basic block and it ends in a conditional jump, in the flattened code, it's going to still end with a jump to that one basic block, and it's going to go back to the state machine, which is going to take it to a basic block, which is going to be the decision basic block, where it actually makes the decision that was originally in the same block. And it makes the decision, and based on that sets the state of the state machine to that of the next state or to the next basic block. So this was generally about pattern matching and the generic algorithm of how you can deal with control flow flattening. And at the end, I wanted to talk about emulation and how to or whether to use emulation. This is both an encouragement and a cautionary tale about using emulation. So as many complex reversing techniques or analysis techniques, it's both good and evil. So it could be a great help if it works, or it could be like an enormous time waster that you wish you didn't even try. So in practice, the goal is to figure out where it's efficient to use emulation. And just a couple of problems with emulation. So it doesn't really run. So obviously, many things are not really going to happen that is being emulated. There is dependency on other functions, which you can decide whether you want to emulate the called functions as well, or you can just make up some kind of values, or maybe the tooling that you're using are going to create some kind of stabs for called functions. But you don't really know what's going to be the output of the called functions unless you really emulate them. Same with the APIs and libraries. Again, tools are often create stubs for APIs and library calls, which might be helpful, but you still kind of don't really know what's going to happen there. And you might run it and it works and that's great, or it doesn't, and then you still need to invest some more time. So in Pandora, where emulation worked well, for one, opaque predicates, because it's something that all the data is there that you need to use to calculate that address for the call. You can easily use emulation for that, because you just need to emulate this part of the function, and once you get to the call, you just need to look at what's in REX, and that's going to be the address, and then you can use that to comment in IDA. So for instance, here I used Flare emu, but there is also Dampulator that you can use for emulation. And this is basically like the simple version of how you can resolve these opaque predicates with an IDAPython script. Basically, in main, we just get the function that we are looking at in IDA, and then we start an emulation from the beginning of the function and create a call hook, and that's the other function you can see. It's basically a callback function that's going to be called whenever the emulator finds a call instruction. And then once it finds a call instruction, your call hook is going to execute, and you can just check the value of area or the value of the whatever register is being used as the target of the call instruction or the operand of the call instruction. And on the right side, you can see the output. So it basically just prints out that I found a call here, and this was the value of the register that's being called. You can extend this script, so that's what I did to basically comment these values back to IDA Pro. You can even add like artificial cross-references from that call to the function that's being called. So you can extend your IDB to be useful in the future with this additional information. Then another use case where emulation worked really well is this string decryption. It was kind of an iterative process, but only because there were 14 different functions. So whenever I found a new decryption function, I just named it as that, and I rerun the emulation on the function that called the string decryption. By the way, you see here the control flow graph of the decryption function. So basically, whenever I saw this same control flow graph, I knew that it was a decryption function. And this is the IDAPython code for emulating the decryption. It's exactly the same until it finds a call, and once the call hook is executed, it checks whether the called address is a decryption function, and if it's a decryption function, then it starts a separate emulation of that decryption function with the inputs that are currently there at the call address. And basically, this way, yeah, you can see that's just how we emulate the decryption function. So it's basically like 3 useful lines in the comment. So it's relatively easy. And at the end, you see that I also wrote back the results of the decryption. So later on, when I was looking at the binary, I would see that, oh, this is the place where it creates the mutex because I see it from the string that's being called or that's being decrypted. So this was very useful. And as I said, it's also a cautionary tale. So I wasted my time, so you don't have to. So even after I did the analysis, I was so intrigued with control flow flattening that I wanted to, work more on the emulation idea. But because it was stuffed with so many different obfuscations, there were always like different problems coming up that things didn't work. So I used emulation on other samples where there weren't so many obfuscation. There it worked well, but in Pandora there were just so many stuff there that it was really hard to create an emulation script that would be generic enough to use on different functions. So ultimately, in case of Pandora, it wasn't very useful. And in this case, for instance, just debugging the sample, like doing the emulation for the other stuff I mentioned, and then debugging the sample was more time efficient than writing an emulation script for the control flow flattening. So, you don't have to waste your time on this anymore. But the point is, like, if you see control flow flattening, once you look at how the other obfuscation techniques are there, you can decide, you can experiment a little bit with emulation. If you get good results relatively quickly, then it makes sense to continue. If you don't, then probably it's better to do the analysis in another way, such as debugging or something like that. All right. So in conclusion, obfuscation is bad. Control flow flattening is bad. Reverse engineering rules. Yeah. Thanks very much. And if there are any questions, this is the time.
Any questions? No questions? No, yeah, I have.
Thank you for the presentations, very interesting. Just one question. Do you know at least the source of those opaque classification or the opaque obfuscations? Is it LLM-based obfuscations, or is it specific compilers, or is it specific tool set?
You mean for Pandora?
Yeah, for example, yeah.
I'm not sure what tool exactly was used for Pandora. There are a few tools out there. I played with Tigris. That's pretty cool. So I really recommend to try that when you write your own binary and then do obfuscation and then see what's the result. Tigris does it on source code level. So it basically creates a new source code that you can then compile, and then you get an obfuscated sample. Also, Tigris offers like a lot of different obfuscations. So what we saw here is the switch case based. There are also much more evil techniques in terms of control flow flattening. So it might extract every basic block into a separate function call, and then you don't have like these control flow graphs anymore because it's going to be just function calls. So yeah, there are quite a few tools. So check out Tigris.
Thank you.
Yep.
Other questions? Okay. Thank you, Geri. Thank you very much.
Thanks very much. Bye-bye.
Thank you.